Hi, this is Osama Al-Amrani. In this episode, I will talk about pressure of liquids, solids, and atmospheric pressure. Have you ever wondered why a raw egg doesn't crack under the weight of a chicken? This is a question that may seem simple at first glance, but it introduces us to a fascinating and fundamental concept in physics: pressure. Pressure, in its most basic form, is a measure of how much force is exerted over a certain area. Think about it this way. When a chicken sits on an egg, the force of the chicken's weight is distributed over the surface area of the egg, which prevents the egg from cracking. This is a prime example of pressure in solids. Now let's imagine we take that same principle and apply it to liquids. When you push down on the surface of a liquid, such as water in a pool, the force you exert is also distributed across a certain area. So why doesn't an egg crack under a chicken, or why can you swim without being crushed? Well, the answer lies in understanding the concept of pressure. So, what exactly is pressure? Picture this. You're trying to pierce a piece of paper with a thumbtack. The pointed end of the tack easily goes through, but if you tried to do the same with the flat end, you'd have a much harder time. Why is that? Well, it all comes down to pressure. Pressure is simply the amount of force applied over a certain area. When you're using the pointed end of the tack, the force you're applying with your hand is concentrated over a very small area. This creates a high pressure, and the paper is easily punctured. On the other hand, when you use the flat end, the same force is spread over a larger area, resulting in lower pressure. Hence, it's harder to pierce the paper. But how is pressure different from force? Let's take a moment to differentiate the two. Force is a push or a pull on an object. It's what you do when you lift a bag of groceries or push a door open. It's a direct interaction that causes a change in motion. Pressure, however, is related to force, but it's not the same thing. It's about how that force is distributed. Imagine you're stepping on a grape. If you step on it with your whole foot, the grape might survive the encounter, but if you step on it with your heel, well, it's grape juice time. In both instances, you're applying the same force, but how that force is spread out changes the pressure. And that's the secret of pressure. It's a sneaky little thing. It's not just about how much force you apply, but also about how that force is spread out. You can apply a lot of force over a large area, and you'll have relatively low pressure. But apply that same force over a small area, and you'll have high pressure. So, in essence, pressure is all about how force is spread out. Now let's delve into how pressure works in solids. Picture a towering skyscraper reaching upwards into the sky. It's majestic, right? But have you ever wondered what's going on at the base? Beneath this architectural marvel, there's a whole world of pressure dynamics at work. In solids, pressure doesn't play favorites. It's perfectly democratic, spreading itself evenly in all directions. But it's also a bit of a diva, increasing with depth. So in our skyscraper, the pressure at the base is greater than at the top. Why is that, you ask? Well, the pressure at any point in a solid object is determined by the weight of the material above it. Think of it as a never-ending game of king of the castle. The particles at the bottom have to support all the others trying to claim the throne. So, they experience more pressure. Now imagine you're a particle near the top of the skyscraper. You've only got a few levels of particles above you. The pressure you're experiencing is relatively low because you're supporting less weight. But as you go deeper into the building, there are more and more particles above you. More weight means more pressure. This is why the foundation of buildings needs to be strong and stable. It's not just about holding up the structure, it's about withstanding the increasing pressure from all the weight above. And it's not just buildings. This principle applies to all solids. Whether it's a mountain, a pile of books, or even a snowman, the pressure at the base is always greater due to the weight of the structure above. This principle of pressure in solids is a fundamental concept in many fields, from civil engineering to geology, and even to understanding how our bodies function. So in solids, the pressure increases with depth, and it acts in all directions. But how does pressure behave in liquids? Well, let's dive in and explore. You see, pressure in liquids, much like in solids, also increases with depth. This is due to the weight of the liquid above pushing down. So the deeper you go into a body of water, the more weight of the water you have pushing down on you, and hence, the greater the pressure. But there's more to it than just depth. The type of liquid matters too. Denser liquids like mercury exert more pressure at a given depth than less dense liquids like water. So, if you were to swim in a pool of mercury, which I wouldn't recommend, you'd feel a lot more pressure at the same depth than you would in a pool of water. Now, let's talk about buoyancy, a fascinating phenomenon closely related to pressure in liquids. Buoyancy is the force that allows objects to float in liquids. It's the result of pressure differences in a liquid. Imagine you're swimming underwater. The water pressure at the bottom of your body is greater than at the top because of the extra depth. This creates an upward force on you, which is buoyancy. You've probably experienced this before, the feeling of pressure increasing as you dive deeper into a pool. The deeper you go, the more water there is above you, and the more pressure you feel. This is why your ears might start to feel uncomfortable when you dive deep in a pool or in the sea. It's the increased pressure exerted by the water at greater depths. So whether you're a deep-sea diver exploring the ocean depths, or just a curious mind eager to understand the world around you, understanding pressure in liquids can give you a fresh perspective on everyday experiences. And that's the wonderful thing about science, isn't it? It helps us make sense of the world in ways we never could have imagined. Thus, similar to solids, pressure in liquids also increases with depth. Let's shift gears and talk about atmospheric pressure. This fascinating concept is all around us, literally. You see, our planet is enveloped by a thick layer of air called the atmosphere. This atmosphere isn't just floating around, it's pressing down on everything due to gravity, and this is what we refer to as atmospheric pressure. Now imagine you're holding a book. You feel its weight in your hands, right? That's because gravity is pulling it down. The same concept applies to the atmosphere. The air above us has weight, and this weight is distributed over the surface of the Earth, creating pressure. Simply put, atmospheric pressure is the pressure exerted by the weight of the air in the atmosphere. You might be wondering, does this pressure have any real-world effects? Well, the answer is a resounding yes. It plays a significant role in determining our weather. High atmospheric pressure typically brings clear skies and calm weather, while low pressure often brings stormy conditions. This is because the air in high-pressure areas is denser and cooler, whereas in low-pressure areas, it's less dense and warmer, leading to the formation of clouds and precipitation. Moreover, atmospheric pressure also affects our body. Have you ever noticed how your ears pop when you're ascending or descending in an airplane, or why climbers need oxygen tanks at high altitudes? That's all due to changes in atmospheric pressure. As we climb higher, the atmospheric pressure decreases because there's less air above us. This can affect our bodies, leading to altitude sickness in extreme cases. So atmospheric pressure isn't just an abstract concept in a physics textbook, it's a tangible force that shapes our world and our experiences within it. From the weather patterns that dictate our outdoor plans, to the physiological responses we experience at different altitudes, atmospheric pressure is a constant and influential presence in our daily lives. So, atmospheric pressure plays a crucial role in our daily life, from changing weather to our body's reaction at high altitudes. Finally, let's talk about how we measure pressure. The standard units of pressure are varied, and each serves a unique purpose. First up, we have the Pascal, denoted as PA. This is the standard unit of pressure in the International System of Units, or SI. It's named after the French polymath, Blaise Pascal. Then, we've got the atmosphere, abbreviated as ATM. This unit is commonly used in chemistry and weather forecasting, and it's roughly equivalent to the pressure exerted by Earth's atmosphere at sea level. Next on the list is the bar, which is used in meteorology and geology. It's about the same as 1 atmosphere, but not exactly. And last but not least, we have pounds per square inch, or PSI. This unit is popular in the United States and in the field of mechanical engineering. So whether it's Pascal or PSI, each unit of pressure has its unique application and context.